Welcome to 7.4 Paired Data T Procedures. Like we did with two-sample data, we are going to look at both the T interval and the T test for paired data. The nice thing about what we're going to do is you've already done it before in its entirety. The only difference is we are finding the difference between two sets of data. So first, let's talk about what is paired data. So data are paired when the observations are collected in pairs or observations in one group are naturally related to observations in another group. Now, once we know that the data are paired, we examine the pairwise differences. So we subtract one from the other, and it is the differences that we care about. So then we go on to ignore the original two sets of data and only use the differences as our sample. So let's go ahead and look at the one sample t interval for paired data. So the first thing you're going to do is you are going to define the parameters. Now this is going to be a little bit different than what we're used to because we are taking two sets of data and turning it into one. And you have to state how you do that. So a couple of important things to note. You have to say the true mean difference. You have to notate how you subtract. And then you want to talk about the quantitative variable and your population of interest. The big key thing that you do not forget is that you include how you found the differences because that does make a difference. So assumptions and conditions are going to be the exact same thing as they were for a one sample t test or a t interval. You are going to check, is it random data? Does the 10% condition get met? And remember, we verify that the population is greater than 10 times the sample size. Both of these things are checking for independence. So the independence assumption is checked by the randomization condition and the 10% condition. Now, if we don't think that the independence can be tested and verified using the 10% condition, we can go on to make a statement that says it can also be stated that there's independence among treatment groups. Basically, our groups are going to act independently of each other and have no influence. The third thing that we check is the nearly normal condition, and you check that in one of three ways. You can see if the central limit theorem works. Is my sample size greater than or equal to 30? You can do a visual representation. If I do a box plot, make sure there's no strong skew and no outliers. Or if you're lucky, it is stated in the problem that the sampling distribution is approximately normal. All of these conditions we have checked before in the one sample t interval. So now we move on to naming the method. So we call this a one sample t interval for paired data. Now, this is the one test where the AP exam likes to switch it up. Sometimes they will call it the one sample t interval for the mu differences. Sometimes they will call it a matched pairs t interval. Now, how you state it, I will try to keep you following the pattern, one sample t interval for paired data, but there is multiple ways you may see this. Now, if you were to write matched pairs t interval on your test, yes, I would give you credit, but I try to keep you in a pattern set. So one sample t interval for paired data is how you will see me write it. Now we are going to move on to calculating the interval. So again, we know point estimate plus or minus a margin of error. So we have our sample mean, and remember the sample mean is based on the differences, not on the individual sets of data. Plus or minus, T star we're going to get from second bars number 4. It's going to ask us for the area. This is going to be based on what size confidence interval we have, and degree of freedom, which we're going to follow the same pattern we did for one sample data, where it's just sample size minus 1. And then we have our sample standard deviation divided by the square root of n. The exact same formula from one sample t interval. This time we are just using our data set as the differences. We can be blank percent confident that the interval from lower bound to upper bound captures the true. Again, very, very important. We're finding a mean difference in the quantitative variable among the population of interest. So I prepared ahead of time, and I have our confidence interval question following the confidence interval portion. So example 1, a researcher studied a random sample of identical twins who had been separated and adopted at birth. In each case, one twin A, was adopted by a high-income family, and the other twin B, was adopted by a low-income family. Both twins were given an IQ test as adults. Here are their scores. So we have the data set for twin A's, and we have the data set for twin B's. We want to construct and interpret a 95% confidence interval for the true mean difference in IQ scores among twins raised in high income and low income households. Now, they don't have any direction in which they're interested in for the differences, so you really could go either way. For this particular problem, I'm just going to do my top row minus my bottom row. So I'm going to do high minus low. So all I did was I went between each pair. So we are pairing the twin with their twin and finding the difference. So 128 minus 120 is 8, 104 minus 99 is 5, 108 minus 99 is 9, and so on for all 12 sets of twins. Now, I want you to remember this data no longer matters. It is not our data set that we are interested in. We do not care about the original data anymore. Our data for this problem is just the differences. That is the only thing I am looking at now. So let's go through the steps of panic. First thing I need to do is define my mu, my parameter. And typically you will note this as mu d. Whether you use a lowercase or a capital D is up to you. Personally, I do the lowercase just because my capital D's start to look like O's, and then I think it's a null mu, and I don't want to do that. So I'm going to say it's the true mean difference. Notice that I stated I'm doing high minus low in IQ scores for identical twins raised in different households. So now that I know what my parameter is, I can go ahead and start checking my assumptions and conditions. I'm going to first find out, I did take a random sample. So I'm going to go through these, and it's going to pull everything up at once, and we'll go over it together. Random sample is stated, and we can assume that there are at least 120 twins like these in the population. That's just an assumption we are going to make. You could also go as far as saying that each pair of twins is independent of each other, or each treatment group is independent of each other. But I do think it's fair to assume that at least 120 twins are out there that may be in a similar situation. Now, for my box plot, I'm going to go ahead and pull up my calculator really fast. And I have my data currently in stat edit edit in L1. So I'm going to go to second, y equals. Now you probably have your plot on, but I'm going to double check and turn mine on. Go to the box plot with outliers. Make sure it says L1 and 1. Hit zoom 9. And I should have a box plot that looks similar to the one I drew. And if I wanted to get the 5-number summary, I just hit trace left, right. So remember, we are just trying to make sure that there is no strong skew. There can be slight skew in your data, but anything extreme you want to avoid. So I can tell from my median to my max and my median to my min, they're approximately the same. So I'm going to state no strong skew. I know that I do not have any outliers. Therefore, we're going to say this is approximately normal. Going to go ahead and name my test, one sample t interval for paired data. And I'm going to go ahead and go through both the by hand version and the calculator version. So my formula, I'm going to pull up. I need my sample mean, I need my critical value, and my standard deviation, and I know my sample size. So first, let's focus on the critical value. I want to build a 95% confidence interval, which means I need to get a critical value to match. So first, I go to my calculator. I go to inverse t, second bars number 4, and I enter in the area of 0.975 because I typically go after the positive t star. If I add my two areas together, because remember your calculator reads left to right, I get 97.5, which translates to 0.975. Degree of freedom is your sample size minus 1, and my sample size is 12. So my degree of freedom for this problem is 11. Approximately, it ends up being 2.2010. So now that I have my t star, I just need my sample mean and my sample standard deviation. So I'm going to pull my calculator up one more time. And remember, we can get that information from stat calc number 1. One var stats, I want it to look at L1, and then I hit calculate. So I get my sample mean is 5. My sample standard deviation is 3.542. So let's go ahead and plug that into our formula. And I went ahead and plugged in my sample size as well. All you have to do now is the addition and the subtraction of these values to get your confidence interval. So this is how you would approach it by hand. Now there is a way to do this in your calculator. So we have done this before because remember, we are running a one sample t interval. Exactly the same. We are still using stat tests number 8. It gives you the option of data or stats. In this instance, we have data. So I'm going to pull up my calculator again, and I'm going to show you stat tests number 8. And then I have data L1, frequency 1. And remember, for the confidence interval, you're going to enter the exact interval that you want. You do not have to do the area thing that we do when we're doing inverse t. And we calculate. So again, it's going to give me a very close, yes, this one matches perfectly, interval, same as we would get by hand. Now remember, you will want to write this all down in order to get credit on the AP exam, and we want to conclude. We can be 95% confident that the interval from 2.7495 to 7.2505 captures the true mean difference, high minus low. Again, I am going in and I am notating how I did my differences in IQ scores for identical twins raised in different households. Now let's look at the one sample t-test for paired data, going through the steps of phantoms. Now, defining the parameters is going to be exactly the same as it was for the interval. We do have to state a null and an alternative. Remember that the null is always the claim that there is no difference. So the calculated differences would be equal to 0, meaning that both populations are equal to each other. So mu of d is equal to 0, and this is what we're always going to write it as. It's never going to change the value. And then your alternative, you have the option of being less than, greater than, or not equal to, meaning there is a difference. We just don't care which direction it is in. Assumptions and conditions are the same as they were for the t interval. Naming the method, a one sample t-test for paired data. Again, they do have that weird, sometimes they write it as mu diff in the actual name on the AP exam. You also may see it as a matched pairs t-test. Now again, I will advise you, just call it a one sample t-test for paired data and you are good. Now we will calculate our t statistic. Remember, this functions just like our z-score did for proportions. Now I have my sample mean minus 0. Remember, this is like our mu naught. We will not write this in my actual calculation of the t statistic in the example. You will see me not include this, but I did include it now just so that you would see I do have this part where I have minus parameter. That's represented by this 0 here. We just don't have to write it every single time. Divided by the sample standard deviation over I know it's kind of hard to tell, but this is the standard deviation over the square root of n, which is the standard error formula that we use in the t-interval calculation as well. Obtaining a p-value, it is going to be dependent on what direction our alternative hypothesis is. If I want everything less than, I shade below. If I want everything above, I shade above. If I have no difference, I'm going to end up with two tails. They are equal in size, so you only have to find one and multiply it by 2. Now, we do get p-values by going to second vars number 6, and it'll ask us for a lower bound, an upper bound, and a degree of freedom. Degree of freedom is just your sample size minus 1. So then you move on to making your decision. If your p-value is less, we reject. If it's greater than alpha, we fail to reject. And we conclude in context as we have been doing since our one proportion z-test. Okay, example 2. Researchers designed an experiment to study the effects of caffeine withdrawal. They recruited 11 volunteers who were diagnosed as being caffeine dependent to serve as subjects. Each subject was barred from coffee, colas, and other substances with caffeine during the duration of the experiment. During one 2-day period, subjects took capsules containing their normal caffeine intake, and during another, they took placebo capsules. The order in which the subjects took caffeine and placebo was randomized. That is important. At the end of each 2-day period, a test for depression was given to all 11 subjects. Researchers wanted to know whether being deprived of caffeine would lead to an increase in depression. The table displays data on the subjects' depression test scores. Higher scores show more symptoms of depression. So they want to know if a person does not receive caffeine, would they end up with a higher score? So we have to kind of figure out what order do I want to do when I'm finding my difference. But let's go ahead and read the question. Does the data provide convincing evidence at the alpha equals 0.05 significance level that caffeine withdrawal increases depression score on average for subjects like the ones in this experiment? So, placebo people do not get caffeine, meaning if what they are claiming is true, I would expect this number to be higher. So I want to work in the positives because that's generally nicer than working with negative numbers. So I'm going to do placebo minus caffeine. And then I find the differences between these subjects. So this time it's not like it was with our t-interval where we had two twins that we collected data on. Now we have one person who took two different treatments. So this one person did 2 days with the caffeine and did 2 days with the placebo, took the test twice. Another example of paired data. So I have all of my differences between my 11 volunteers. I'm going to go ahead and start my steps of phantoms. The first thing I want to do is define my parameter. Mu of d is the true mean difference. Again, very, very important that you notate how you calculated your differences, placebo minus caffeine in depression test score among subjects like these. Now, the null and the alternative. The null is easy. You know it's always going to be mu d is equal to 0. The alternative. Now, here is where the AP exam is very flexible. Say, for instance, you were fine with working with negative numbers and you did caffeine minus placebo. That is okay. However, if I put caffeine first, I would be expecting this to be less than 0 because I would have negative values. Now, since placebo minus caffeine is what I'm working with, I expect it to be a higher number. I expect it to be greater. So my alternative is mu of d is greater than 0 because remember, higher scores show more symptoms of depression. Now that I have my null and my alternative, I'm going to go through and check my conditions. So I don't necessarily have that random sample possibility because I'm dealing with volunteers, but the order of treatments were randomly assigned. I can also say that my treatment and my group subjects are independent, meaning they are acting on their own. One result does not necessarily affect another. Now, with my box plot, I'm not going to go through the calculator steps again just to save some time, but I did put my data into L1, ran my box plot, traced my 5-number summary, and I don't see any strong skew, and I did not have any calculated outliers, so I'm going to call this approximately normal. Name of my test, one sample t-test for paired data. And then we run through our calculator and our by hand method. So first thing, going to pull up my formula. I need my sample mean and I need my sample standard deviation. So I will again remind you of how to do that. Stat, calc, and my data is currently in L2 for this one. And I get my mean 7.3636, standard deviation 6.9177, and I have my sample size, of course. Remember, again, let's recall, let's even cross it out. We are no longer dealing with the original data. It is gone. It does not exist in our brains anymore. We are only dealing with this one sample set of data of calculated differences. This is what is currently in L2 for me. This is what I just ran stat calc 1-bar stats on. So I have my mean, my standard deviation, and my sample size. Plug this into my calculator. Be careful. Remember, this is standard deviation over square root of sample size. I get approximately 3.5304. Now that I have my t-statistic, I need to get a p-value. So I always like to sketch a picture. Remember, your direction is based on your alternative hypothesis. I am saying this is greater. My mu of d is greater than 0. So I want to shade everything above my t-statistic. Now, in order to get this area, I do have to go to my calculator again, go to second vars, and I need to go to TCDF. And it's going to ask me 3 things. It's going to ask me lower bound, upper bound, and degree of freedom. So my lower bound is the t-statistic. My upper bound is infinity. Remember, we enter this into our calculator as 1E99. And my degree of freedom is my sample size minus 1, which in this case is 10. And if you forgot where to get TCDF, it should be second vars number 6. And this gives me approximately 0.0027. So this is my p-value for this problem. Now, if you wanted to take the approach of, I just want to put it into my calculator and get the p-value, you can do that. You're going to go to stat, tests number 2. And this time, again, you're going to have the option of data or stats, depending on what your question gives you. You will be given what's mu0 for both, and you'll always state it's 0 for matched pairs or paired data, whatever you want to call it. Data asks what list, frequency we leave as 1, and then it asks you what your hypothesis is, your alternative. Stats will ask for your sample mean, sample standard deviation, sample size, and also ask what the alternative hypothesis is. So I'm going to pull my calculator up. Let's go to stat, tests number 2, and I have data. My mu is going to be 0. That's my null. Remember, we always say it's mu of d is equal to 0. This time, my data is in L2, so I'm going to hit second 2. Frequency, I'm going to leave at 1. And this time, I want to say that mu is greater than 0. So I'm going to select my last option, mu greater than 0. Calculate. And I get t is 3.5304, exactly the same. P is 0.0027, exactly the same. And like with any calculator method that you use, you write everything down that is on your output screen. Once we have our p-value, no matter which way you got it, conclude. Since our p-value of 0.0027 is less than alpha, we reject the null. There is convincing evidence that caffeine withdrawal increases depression on average for subjects like these.